Okay, good day. Do you hear me?
Yes.
And do you see my presentation?
Yes, it's okay. Good.
Okay. So, good day, everyone. Today I'm going to speak about the derivatives of the derivative of ytterbium compound, which consists of a redox active ligand of DPP-BIAN. Redox active ligand is the ligand that can directly participate in chemical transformations. It could react either as electron storage, providing electrons to the substrate, or it can form a chemical bonds with the substrate directly. These possibilities of redox active ligand was shown a lot of times for a main group products, for a main group elements, for example, for gallium and aluminum compounds. These compounds were active against various organic substrates and small molecules, and it is not only activates small molecules, but sometimes these compounds were found to be to activate molecules and small molecules, and it can push the reaction further. The activated small molecules could be modified in the reaction sphere of the metal atom further. In this regard, lanthanides atoms are quite different from the main compounds. It is well known that the lanthanide compounds can as well activate various organic substrates or small molecules to give, for example, dithionite or sulfate complexes in the coordination sphere of bulky cyclopentadiene dienides could be formed new chemical bonds. The new idea that we propose that the complex interplay between the redox active ligand and the low valent ytterbium atom may result in the redox isomers. It asked the compound which consist of different physical and chemical properties. At the same time, they have a same components. And this idea was proved by the synthesis of ytterbium chloride and ytterbium bromide, which exhibit the genuine lanthanide redox isomerism. So we decided to expand this idea to other compounds and to see if there are possible some other redox isomerism cases. The first very stunning reaction was obtained by the treatment of BIAN ytterbium by trimethyl azide, which results in hexanuclear crown compound, which consists of 6 ytterbium atoms and 6 bridging N3 groups. But there is possibility to generate isomers. For example, one of the electron from the BIAN ligand could go to the ytterbium atom to give the ytterbium-2 compound. But in fact, that was not the case. The magnetic chemistry investigations show that among all the temperatures from 0 to 300 room temperature, the compound is hexanuclear ytterbium-3 compound. So as to prove this compound, the synthesis of this compound, another reaction was proposed by the synthesis of this compound was proposed by the salt metathesis reaction. On the first stage, compound 1 was treated with iodine, half of the equivalent of iodine to give B-ytterbium iodide, and salt metathesis reaction should give some the compound 2. But in fact, the compound 2 is the main compound of this reaction, but there is also a very small amount of another compound, compound 3, which is ytterbium azide, and it is a molecular polymer with a bridging sodium and N3 groups. This compound, according to the X-ray structure, the bond distances among the metallocycle, there is no doubt it is an anion radical compound. Another reaction was obtained. Another reaction product was obtained by the treatment of the B-ytterbium with phenyl isocyanide, which is electronically isostructural to the trimethyl azide. Yeah, but in this case, the reduction of the compound happens and a new carbon-carbon bond is formed. This compound is consists of B-ion ligands in the dianionic state and the terbium atoms in the state of +3. The reaction with small molecule N2O results in a product with a very low yield. Probably this is because on the first stage, another compound is generated. The long reaction time shows that another intermediate is formed on the first stage, which has a few possible decomposition ways. And one of these ways results in compound 5. Simultaneously, a lot of the neutral DPP-BIAN ligand is formed. The reaction with small molecule of ammonia results in evolution of dihydrogen and formation of corresponding imide. Again, this compound consists in all temperatures consists of dianionic DPP-BIAN ligand and the ytterbium +3 atom. The treatment of compound 1 with tetrafluoroethylene results in isostructural compound 7, which is very close to the previous compound. As I told earlier, the compounds of the derivatives of chlorine and bromine has a shift in the magnetic shift of the magnetic moment at 150 Kelvin, but the compound 7 doesn't have this shift, and it consists in the single form of the ytterbium 3 derivative. A very tricky compound was synthesized. While the synthesis of the main compound 1 was investigated. Among the great amount of crystals of compound 1, there was a very small amount of bright red crystals of 8. The synthesis of this compound wasn't simple, and so as to reproduce the synthesis of this, we tried to generate a very active ytterbium metal from the corresponding ytterbium diodide, from the equivalent of ytterbium diodide and 2 equivalents of potassium graphite. And in reality, this resulted in a quite high yield of compound 8. This compound is tricky because there are possible 3 isomers. One of the isomers should consist of BN -3, and another possibility is where the DPP-BIAN is of oxidation state of -4, while one of the terbium atoms should be +2, another +3, or vice versa. But in fact, magnetic chemistry shows that this compound again preserve both atoms in the +2 state, and the magnetic moment of the compound is very close to 173, which stands for anion radical 3- state of the BIAN ligand. So I'd like to draw a conclusion that the BIAN terbium compound activates a number of organic substrates and small molecules. The DPP-BIAN terbium exhibits reducer function in all of this reaction. It's either due to the BIAN ligand or the terbium atom, and lanthanide redox isomerism appeared to be a very susceptible to the environment of the lanthanide atom. I'd like to say thanks to everyone who have helped with doing this work, and you, my dear colleagues.
Thank you, Vladimir, for your interesting lecture. Do you have some question?
It seems no.
Yeah, sorry, I have a question.
Yes,
I don't know
yes,
how
Fabrice.
to raise my hand. Very nice talk and very nice compounds. I have just a simple question. Did you try to check the dynamic magnetic properties of your compound? Because you show us some static magnetic properties, but in a dynamic point of view, several of your compound could be very interesting.
Not yet, but we have plans to do it.
Okay. But it should be very interesting because you have very unusual environment around your terbium-3 compounds, and sometimes your trivalent lanthanide is associated to a radical, and so exchange interaction could suppress the quantum tunneling of the magnetization that we have often in case of terbium compounds. So I think you have very nice compound in your hands to have very nice dynamic properties.
Yeah, exactly. Yeah.
Okay, Vladimir, thank you for your lecture. One more. We will move to another one. Yeah, please switch off. Yes.
Mm-hmm.
Yes. Let me introduce next speaker, Dr. Maxim Chegerev. He worked in the Institute of Organometallic Chemistry, and now he moved in Rostov-on-Don in Federal University, and he will present his lecture titled "Spin Transition in Catecholate Iron-Free Complexes with 3-pyridyl-methyl-amine derivatives."
Good afternoon, dear colleagues. It's okay?
Yes, we hear you.
Thank you. Good afternoon, dear colleagues. First of all, I would like to thank the organizing committee for the opportunity to be a participant of this event and give a talk here. I will present the results of comprehensive study of spin transitions in catecholate ferric complexes with 3-pyridyl-methylamine. The development of molecular materials on the basis of open shell coordination compounds with magnetic properties variable by external stimuli represents one of the most interesting areas in modern inorganic chemistry. Such polyfunctional species possesses far-reaching prospects in their versatile application areas, from sensors and displays for molecular switches, molecular memory, and spin quantum bits. Spin crossover and valence tautomerism are the most common and studied mechanisms of magnetic instability that control changes in the spin states of transition metal complex. The spin crossover phenomenon is caused by the rearrangement of electrons inside the valence shell of the metal ion and is usually observed in complexes of divalent and trivalent iron, but also it occurs in some cases in cobalt systems. Valence tautomerism is characterized by a reversible intramolecular electron transfer between metal ion and the redox active ligand, and has been studied in most detail in cobalt complexes with orthokinons. Recently, this phenomenon for the first time was observed in tin complexes with redox active iminokinons. A widespread structural motif of metal complexes manifesting spin crossover or valence tautomerism are the ionic systems comprising one orthokinon redox ligand and tetradentate and donor base. The iron and cobalt complexes are mostly studied in this field. While iron complexes in such environment demonstrate only spin crossover, in case of cobalt complexes, compounds showing both valence tautomerism and spin crossover are found. Along with this, it was found that such ferric catecholates are effective catalysts for the oxidation of catechols with oxygen. We started our research from iron complexes based on available 3,6-diterbutyl substituted catechol and TPA. Since these systems are ionic, we additionally varied the possible counterions. Preliminary DFT results revealed the possibility of spin crossover in systems under consideration. According to calculations, the energy difference between low spin and high spin states does not exceed 10 kilocalories per mole, which, within this approximation, indicates on the high probability of detecting the spin crossover. At this slide, we can see the synthetic approach used for preparation of complexes 1,4. At the first stage, ferric chloride was reacted with TPA, and further reaction with deprotonated catechol is accompanied by the color change from the yellow to dark blue-violet. Metathesis reactions with corresponding salts results in precipitation of desired compounds 1 to 4 as the dark blue crystals. In case of complex 3, ferric perchloride was used as a starting material. Compounds were isolated in high yields, about 90%. According to X-ray diffraction analysis, complex 1 was found to be unsolvated, while complexes 3 and 4 contain a half of solvate water molecule. Metal center in all 6 coordinate iron complexes possesses distorted octahedral geometry composed by 4 nitrogen atoms of TPA ligand and 2 oxygens of catecholate. The molecular structure were determined at 2 temperatures. Metrical parameters collected at 300 Kelvin clearly indicates on the inclusion of the metal center in complex 1 in the high spin state. The average interatomic distances are characteristic for previously described high spin ferric catecholates. The CO and CC bond lengths in the redox active catecholate ligand indicate on the dianionic nature of the redox active ligand. In 2012, Professor Brown has proposed to use the metrical oxidation state approach to determine the redox state of dioxalines. The calculated Mohs index for complex 1 is -0.8, which allows us to refer it as a catecholate. Deviation of calculated Mohs from -2 points to the small semiquinone-like alteration of catecholate bonds. Such distortions were discussed previously and were explained as a quantum mixing of ferric catecholate and ferro-semiquinonate electronic configuration. DFT calculations are in a good agreement with this assumption. The part of spin density from the ferric ion is delocalized over neighboring oxygen atoms. It's caused by the mixing of some close by energy catechol and d metal orbitals. Lowering of the temperature does not significantly change metal donor atom bonds in one. The average bond lengths are slightly shorter than obtained at high temperature, but longer for known low spin ferric catecholate. Such relatively small bond contraction can be explained by appearance of the low spin fraction due to incomplete spin crossover in complex 1. This assumption in a good agreement with magnetic and Moss-Bayer data, demonstrating the ratio 92% high spin to 8% low spin at 100 Kelvin. Heat T is almost constant in over all the temperatures, and the small minor lowering of the heat T can be explained by the presence of the low spin fraction at this temperature. Moss-Bayer spectra at high temperature exhibit well-resolved quadruple doublet comparable with corresponding high spin ferric state. Subsequent lowering of the temperature is accompanied with the appearance of other quadruple doublet in addition to the observed at 300 Kelvin, which is characteristic for the low spin ferric isomer. The ratio of intensities of two signals was estimated as 90% to 10%, indicating on the incomplete spin crossover. Unfortunately, we were unsuccessful in obtaining the single crystals suitable for X-ray diffraction for complex 1. Nevertheless, the geometry of complex 2 was obtained from the DFT calculation. It should be noted the obtained structural data are close for compound 1. Magnetic susceptibility of complex 2 at high temperature is close to found for 1 and points to the pure high spin state. At lower temperatures, Heat shows a gradual decrease, and in this case, incomplete spin crossover takes place, and high spin to low spin ratio was estimated 50 to 50 at 30 Kelvin. Detailed analysis of Moss-Bayer data confirms this estimation, indicating the presence of 55% of low spin state with the mixture with 45% of high spin state at given temperature. Analysis of the metrical parameters in compound 3 collected at 300 Kelvin clearly indicates on the high spin state of the iron center. The Mohs parameter for 3 amounts for minus 1.77. Significant changes of metal donor atom bond lengths were found in complex 3 collected at 100 Kelvin, caused by high spin to low spin conversion. Spin transition is accompanied with the shortening of the characteristic interatomic distances. The calculated Mohs index at low temperature indicate on the catecholate nature of the redox active ligand, but in comparison with Mohs collected at high temperature, the alteration of the CC bond is slightly larger, which reflects the stronger quantum mixing of ferric catecholate and ferrous semiquinonate configurations at cooling. Analysis of magnetic data has shown that more substantial changes in magnetic susceptibility. Similar to mentioned above, the high temperature Heat values are close to the high spin state. Magnetic susceptibility shows a insignificant lowering in the temperature range 300, 170 Kelvin, but further cooling is accompanied with the sharp decrease of the magnetic susceptibility at 100 Kelvin. This value is characteristic for low spin catecholate ferric systems with doublet ground state. The Moss-Bayer spectra at 3 Kelvin exhibit Moss-Bayer spectra of complex 3 at 15 Kelvin exhibit two well-resolved doublets. The measure species accounts for 95% of low spin ferric fraction in the sample. The minority species with 5% of relative area were assigned to the high spin ferric 3 component. The high temperature spectrum is unambiguously referred to the pure high spin state. And thus, in the case of compound 3, we can conclude that virtually complete spin crossover transition takes place, and only 5% of molecules are trapped in high spin state at 50 Kelvin. X-ray data on complex 4 collected at high temperatures indicates on the high spin state of the metal center again. The calculated Mohs for complex 4 is minus 0.71. Interestingly, the calculated Mohs index in this case is the lowest among the studied compounds. Significant changes again were observed of metal donor atom bond lengths at low temperature due to high spin to low spin conversion. With the aim to shed light on the electronic structure of the low spin isomer of compound 4, the X-band hyperspectroscopy measurements were performed. Previously was shown that electronic structure of the redox active ligand directly affects on the degree of delocalization of unpaired electron over the metal cycle, and therefore contribution of two possible states, ferric catecholate and ferrous semikinonate respectively. The corresponding spectra of low spin isomer was registered at frozen methylene chloride solution at 100 Kelvin. The low spin signal is shown to be pseudo-axial. Anisotropy was estimated as a difference between these two values and amounts to 0.145. It should be noted that in comparison with the previously published data for 3,6 diturbital substituted catechol, in our case, we found that increasing contribution of the semikinonate ferric state, ferrous state, in contrast to the well-known catecholates. Analogous to complex 3, magnetic behavior was observed in complex 4. Heat values almost unchanged in the temperature range 300, 200, and at lower temperatures demonstrate a sharp decrease to reach a plateau typical for the low spin ferric configuration. Slight deviation of obtained low temperature values can be explained by the presence of about 10% of molecules trapped in high spin ferrous state at this temperature. It should be noted that the analysis of the magnetic susceptibility data do not allow one to unequivocally distinguish two possible ferric catecholate and ferrous semikinonate electronic configurations, which are characterized by the same multiplicity. And unexpected result was obtained after detailed analysis of Mössbauer data. At high temperature spectra is characterized by presence of two doublets. The first one corresponds to the high spin ferric configuration, while the second one, surprisingly, was attributed to the high spin ferrous ion. The relative areas of these two signals are estimated are almost equimolar mixture at 300 Kelvin. Further lowering of the temperature is accompanied with the appearance of the additional doublet belonging to the low spin ferric fraction. In the temperature range 160-100 Kelvin, the almost complete spin crossover transition takes place. High spin ferric to low spin ferric. Analysis of obtained results allows us to assume that all changes found in complex 4 can be divided into two elementary steps. First, the almost complete spin crossover transition in the temperature range between 50 and 170 Kelvin, and then valence tautomeric transition, high spin ferric to high spin ferrous above 170 Kelvin, leading to the formation of the ferrous semikinonate isomer. This finding, to the best of our knowledge, makes compound for the first ferric catecholate system of this type, demonstrating valence tautomeric transition in the solid state alongside with the spin crossover. To sum up, the complexes of type TPA iron catecholate with different autospheric counterions were synthesized and characterized. They were found to form a family of systems exhibiting spin crossover processes in the solid state. In the case of complex 4 with tetafluoroborate anion, valence tautomeric transition along with spin crossover takes place. To the best of our knowledge, it is the first example of valence tautomerism in such type iron complexes in the solid state. I would like to thank the Russian Science Foundation for supporting this work, and all you for the attention. Thank you.
Thank you. Thank you, Maxim. Anyone have questions?
Mikhail, we raised our hands, me and Viktor Ivanovich Chegerev.
Oh, yes, of course, but I can see it. So maybe if you have, please let us.
Viktor Ivanovich,
Viktor Ivanovich, please.
You can. It seems to me that Sergey was the first. Excuse me, Maxim. Can you go back to the slide number 11?
This one.
Oh, yes, this one. What is the reason for residual signal of high-speed iron? Is it a mixture? Is it defects? What do you think? Because it's stable signal below 150. Is it no, below 100? 5%. What is the reason for so stable signal of high-speed iron?
Well, thank you for your question. This situation when a small amount of the high-spin molecules trapped at low temperatures, it's usual situation in a lot of spin crossover compounds or in case of iron. And I think it's a few molecules trapped due to maybe some structural reasons in the packing. It should not be impurity as we think.
Okay, this is something like defects in the structure.
Yeah, so we think so, yes, that it's some defects in the crystal structure which trapped a few small amount of molecules in high spin state.
Okay, thank you.
Thank you.
Maybe this is impurity. Oh, Maxim.
Oh, hello.
Yes, Maxim, may I ask you, maybe this is impurity, because I think that molecule will change spin state, but the presence of some impurity of other iron complex, for example, maybe 5% in your case will change the situation. If you check it.
So the Mills-Bauer data is the most precise in case of iron compounds. And as we talk, as I talk with my colleague Mills-Bauer spectroscopy, so he said that it's not impurity. It's trapped in high spin state. It's not impurity because he don't need to use other doublet when he feeds this experimental data.
Okay, thank you. Maybe someone have more questions?
I still have a question.
Okay, Sergey.
Maxim, thank you very much for a very nice talk. I have a question. So about this slide and slide number 14. So please pay your attention to the curve of KT, yeah, and especially around helium temperatures. So on the previous compound, we see a plateau which goes almost to 0 K, I would say, yeah. And the one you showed on slide number 14, we have some decrease of magnetization. So did you try to analyze it, spin distribution, intermolecular contacts, and does it influence high temperature spin crossover transition? Thank you.
Thank you for your question. Yes, in these all cases, different. From the first point of view, it's different. But in case of compound 3, here, we have only 5% of molecules trapped in high spin state. And if we see at lowest temperatures, we see small decrease sharp, about 0, I think, maybe here. As I know from the literature in such type compounds, this sharp decrease explains in the hyperfine splitting. And molecules trapped in high spin state at these temperatures gradually undergo sharp decrease of the magnetic susceptibility. In case of compound 4, it is more substantial due to the more percent of the molecules in high spin state we have at this temperature, 9 and about 13%. And it means that it results in that plateau is located at higher magnetic susceptibility, and the more sharp decrease we observe due to the biggest concentration of the high-spin molecules, high-spin state. And as I said, in most of cases I saw it's explained by the hyperfine splitting. Zero field splitting. I'm sorry. Zero field splitting. Yes.
Thank you.
Thank you.
Okay. Yes, thank you. Yes. Okay, I want to thank Maxim for his interesting lecture. And it was last lecture on this day, on this section. It was last section. Yes, maybe organizing committee have some information.
We just welcome you to join us tomorrow. Looking forward, and so now we just stop recording the scientific session, and actually I would just close this session. Yeah. Okay. Thank you to everybody.
Okay, thank you. See you tomorrow.
See you tomorrow.
Thank you.
Thank you for all.